now we start. So our first lecture is on probability and random process. So why we choose probability and random process? Because this is the basic and core of all tracking things. So if we learn this properly, you will see that everywhere, all paper, all material, they are calling PDFs and they are joint, marginalization, lot of terms. So we thought that it will be better to just go through and just 1 hour I scheduled, but it might take a little bit more. And this course I used to teach in 40 lectures. So, but 1 hour I have to summarize because we don't have. So I start with the beginning, this probability. So we know all those things. So quickly I'm just brushing this. So in probability starts with experiment. Is it visible? You can see. So probability starts with experiment. So experiment is the procedure we perform. It might be thought also. Sometimes we think that experiment means some hardware will be there, something will be there. No, it might be thought experiment also. And that produce some results. So experiment, what it consists of? A procedure and results. So experiment has procedure and there is some results. So then outcome, we call it zeta. It is a possible result of an experiment. We did an experiment, there is some result. So this is called the outcome. Event, an event is a certain set of outcomes. So there are outcomes, and if we create a set of the outcome, then it will become event. And sample space, it is a collection of all set of possible outcomes of an experiment, right? And there is two terms it is written: collectively exhaustive and mutually, it's wrongly written, collectively exhaustive and mutually exclusive. It's wrongly written. Mutually exclusive, that means if one event occur, other will not come. That is mutually exclusive. And collectively exhaustive means if you consider all the event, it will lead to a universal set S. So now if we give an experiment, let's say rolling a die is an experiment, so we call it E. The possible outcome could be 1 or 2 or 3 or 4 or 5 or 6. And the event A, we can define event A in many ways. So event A, you can define it that outcome is an odd number. So whatever outcome is an odd number, that is an event. And what is the sample space? Means collection of all outcome. So 1, 2, 3, 4, 5, 6. You see it is collectively exhaustive. So 1, 2, 3, 4, 5, 6. Nothing can come other than this. And mutually exclusive. That means if one comes, two cannot come. Okay, mutually exclusive. So let's proceed quickly. So now the axioms of probability, that means we cannot prove it. We axiom means we cannot prove it. We assume it and we start with this. So probability could be greater than 1, greater than 0. And if the sample space is yes, so then probability of occurring all the sample space is 1. That means 1 means certain event, it will occur, and 0 means it will never occur, and probability will lie between 1 to 0 to 1. And if A intersection B is null set, then probability of A union B will be equals to probability of A plus probability of B. We all know it. Just I am trying to brush up. So then theorem, this you see, probability of A bar will be equals to 1 minus probability of A. We know it. And then the theorem is if A is a subset of B, then probability of A will be less than equals to probability of B. Now relative frequency approach. Sometimes we say that without the thinking with the relative, with the experiment, real experiment, we can make what is the probability. For example, if we want to see what is the probability of getting head, if we toss a coin, then what we can do, we can toss a coin many more times, infinite times, and we can count the head. This we used to do in our childhood. And then if it is 10 number of samples, we'll see that maybe 8 head comes and 2 tail. So we are confused that, okay, so many, then probability is not matching. But if you do it more, 100, you will see that it's coming half and half, more or less. Then 1,000, 10,000, then you will see that it's coming more or less half and half. So limit n tends to infinity, n is the number of trial, is some event occurring of sub event Na by the all the numbers of events. So this is called the relative frequency approach. So we can do it. So now joint probability is the two events A and B happening simultaneously. Okay, two events, if they happen simultaneously, suppose for example we are rolling 2 die and 1 comes in another die, 2 comes in another die, so it will be so then So then, so we can denote these two events, simultaneous event A and B, A comma B or A intersection B. That means both events are happening simultaneously. Mutually exclusive, that I told that it is probability of A intersection B or probability of A comma B, which is simultaneous event, but they will never occur. So it is null set, probability of null set is 0. Right? Then this is interesting, conditional probability. So how do you say conditional probability? P A slash B. That means probability of A when B, event B has already occurred. We know it. So that is the conditional probability. So we know that conditional probability is P of A comma B. That means two events simultaneously divided by PB. That means if B has already occurred, your sample space is becoming B only. So then you are doing among this B, you are taking when this A will occur. Okay, so your sample space is getting squeezed. Okay, so conditional probability increases because the sample space is getting squeezed. So now mutually independent event. So if you have any doubt, just stop me and ask. Okay, so these are very basic. I tried to summarize all. So mutually independent, what we say, the occurrence of one has no effect on the other. For example, if we take two coin, we toss it, occurrence of one, head or tail, it has no effect to the other. Okay, so that is mutually independent. But mutually independent, it comes that probability of A slash B, that means A condition B will be equals to probability of A because it has no effect. So B occurs or it does not occur, there is no meaning. So probability of A. And from the formula of conditional probability, we can say P of A comma B equals to PA into PB. Okay, both the multiplication. Now Bayes theorem, which is very important. So Bayes theorem says that conditional probability P of A slash B will be equals to P of B slash A into PA by PB. So theorem proof I am not coming. So this is very important theorem. We'll see that from the Bayes theorem only we start doing estimating the states and PDFs. Okay. So another important theorem is the theorem of total probability, which is suppose B1, B2, Bn is a mutually exclusive event and collectively exhaustive. That means if your sample space is like this, okay, and let's say B1, B2, B3, B4 like this, and you have A, this set. So that means if you see that probability of A, that means probability of A intersection B1 into probability of B1 into probability of A intersection B2 into probability of B2, all sum of this. So this is called the total probability. Now if we see PA is this and we can replace the Bayes theorem here in B, so that we can replace P of A slash B into PB. So P of B slash A, BI, that means individual B. So this is another form of Bayes theorem. So we'll see that this also we usually use it. So now if we see what is the meaning of random variable, it's very interesting concept. So I think all of you know it, but as I am brushing it, so let me do it. So suppose we are doing an experiment. So an experiment outcome could be, let's say, zeta 1, zeta 2, zeta 3, so on, zeta n. And we are making a function such that it's mapping it to a real number, okay? So we make a function f of zeta, which makes it say f of zeta, which x equals to f of zeta, which makes it a real number, okay? So that means the outcome we associate with a real number. That is random variable, okay? So if I say that, let's say one example, that if the outcome is, let's say we roll a die, so it could be 1, it could be 2, it could be 3, it could be 4, it could be 5, it could be 6, and if we associate by some rule that if 1 comes, it will be 100, if 2 comes, it will be 200, like this. So we have a real number which we assign to the outcome. That is called the random variable, okay? So why it is variable? It's a real number, it's a variable. Why it is random? Because its outcome is random. So that is the, so we used to ask students, so this concept should be clear here. So for example, the if we do a roll, if we do a coin, if we toss a coin, then what will happen? We may get head or tail, and then there are two outcomes. So with head, I say that if head comes, it is 50. If tail comes, it is minus 50. In book, always it says that the head comes 1, tail comes -1 like this. Not necessarily. We can assign any real number. Okay, and that becomes our random variable. Now, for the time on, we'll forget about the experiment, we'll forget about the outcome, we'll go with the random variable because with the outcome we associate a random variable. Now we'll go with the random variable only. Now let's see probability mass function. What is that? Suppose you have the probability mass function like this. So here I want to say, so let's say the probability mass function we call P. P means probability, okay? Px of x, okay, of a random variable. Here notation is this is variable, okay, random variable. And this is a number, okay? P of x, that means probability of the random variable x taking a value small x. This notation always, okay? It's initially it is confusing, but this is the notation, okay? So what is the probability mass function? Suppose we have a random variable and we assign some probability. Let's say here we roll a die, we get 1, 2, 3, 4, 5, 6, and then we assign a number, say 100, 200, 300, 400, 500, 600. And then, so these are the random variables. So here we do 100, 200, 300, 400, 500, 600, right? And what is the probability of getting 100? Random variable 100 is 1 by 6, right? So it's 1 by 6, 1 by 6, 1 by 6, all 1 by 6. So this is probability mass function. If you have the random variable and if you have the probability, this is the probability mass function. So few important notation is that, so if we do, so probability Px of x should be in between 0 to 1 because it should be. And then sum of all weight should be 1. So probability of Px of x, that is what written, Px of x will be equals to 1. So later we'll see during the estimation how we generate this probability mass function. Estimation is the full of probability mass function. So probability mass function means we have a random variable and we have a probability assigned with those random variables, and then with those random variables, with the probability, it creates a probability mass function. Few properties, this probability could be greater, this would be greater than 0 to greater than 0, equals to 0, or less than equals to 1. And all probability is called sum of all probability is 1. So now if you see that sum of all probability is 1, sometimes later part will tell this weight, this is weight. Probability of random variable we will call weight in later part. Okay. Now it's a probability. Now it's interesting, CDF and PDF. CDF means cumulative distribution function. So cumulative distribution function of a random variable x, fx x, that is interesting. So fx small x, right? So fx small x, I don't know, is it looking small x or not? So, but f capital X small x, that means the CDF of f with random variable capital X at the point small x. What does it mean? It means that probability of x is the variable will be less than equals to small x. Okay, so if I say here that what will be the probability CDF of p less than x less than equals to 500. So it will be 1 by 6 plus 1 by 6 plus 1 by 6 plus 1 by 6 plus 1 by 6, 5 by 6. Okay, so this way it will go. Now probability density function. This is another interesting concept. So probability density function is a very interesting concept. So it says that suppose we have, so it is written like this. So these notations are very fixed. P or PR is the probability mass function or probability. Then capital F X X. This is CDF. Okay. Then small x X X. This is PDF, probability density function. Okay. So this is variable and this is a number. Okay. This notation you have to follow. So now what is the PDF? PDF means you have a random variable x and you have assigned a probability density function. So this is PDF such a way that it is the derivative of the CDF. Not only that, so we generally used to follow this, that it will be, so if we want to calculate the probability, let's say A to B, random variable X, which is between A to B, we do calculate the area under the curve. So students have some misconception. If I ask in Viva, what is the PDF, what is the plot in y-axis, 90% students says that it is probability. It is not probability. It is probability density. If you want to go for probability, you have to integrate. Okay. That is the reason. If you integrate some curve, you'll get probability. So that curve is probability density, not the probability. Okay. So, and then there are nice properties that fx x greater than equals to 0, it has to be. And then fx x dx integration minus infinity plus infinity should be 1, because the all probability should be 1. And then fx x minus infinity to x is the CDF values. And whatever I discussed, a to b fx x dx is the p of a less than x less than equals to b. So that's all. So PDF we will use more frequently. Very frequently we will use PDF. Now we go to the Gaussian distribution, because this is very helpful. In one dimension, it's very simple. We can write it 1 by root 2 pi sigma square. All of us know it. E to the power minus x minus m square by 2 sigma square, where m is the mean. Sometimes in book, mu is written as the mean, and sigma is the standard deviation. Sigma square is the variance. So Gaussian PDF is a bell-shaped curve, right? We all know it. So it's a symmetrical around the mean. Okay, mean m. And where is its mode? At mean only. And what is median? At mean only. And what is the skewness and kurtosis? It's 0. So it's a two-parameter distribution, only mean and covariance or variance we can do. Now, if we go with the conditional PDF, this is another interesting part. Conditional PDF means the PDF, the conditional probability of a random variable x, condition on some event A. Okay, some event has already occurred. So we call it f of x given A. That means conditional of A of small x, which is limit epsilon tends to 0, x within x is within small x plus epsilon slash A. That means A has already occurred. So probability of that, and then limit epsilon tends to 0. So that is conditional probability. That means what is the PDF? What is the conditional PDF? That means what is the PDF when already one event has occurred. Okay. So now let's see one example. So this is an interesting example. A PDF is given by 1/3 e to the power minus x by 3 ux. Calculate the conditional probability, conditional PDF for x greater than 2. Okay. So what is that? So that means we need to know what is the probability of x greater than 2. That is very simple. 2 to infinity, 1 by 3 e to the power minus x by 3 dx. That is coming e to the power minus 2 by 3. And then what is the PDF of x given x greater than 2? That is fx of x divided by the whole sample space. What is the sample space? Sample space is p x greater than 2. So then we will get 1 by 3 e to the power minus x by 3 by, what is the probability x greater than 2? E to the power minus 2 by 3. So we will be getting 1 by 3 e to the power minus 2 minus x by 3 u x minus 2. So you see that it is from 2 to a step function. So the probability will increase, PDF value will increase, it will become peak. So later also we will see when we will do conditional probability, then we reach a peaky probability. That means we reach near some expected value. We will come to later. So now these are very standard formulas. So I think all of us know. So expectation of a random variable x with a PDF fx x is e of x equals to minus infinity to plus infinity x fx x dx. So I told that. So small x means the value, x means the variable, and x is the variable. So expectation of x means x fx x dx. So fx is the density function which it is following. So whenever we are, so I was starting or reading this probability, I was confused, because you see that expectation is mean, right? But again, how this probability density function is coming? We read that mean means you add all them and divide by this, right? But then how this PDF is coming, we are doing so many things. Is it really mean in sense? So the thing is, it is really mean in sense, because why we are doing this? Because in our class 5, class 4, class, what we do arithmetic, we say that in a class there are 20 students and their height is this feet, this feet, this feet. What is the average? So we sum and divide by 2. We are doing the same thing. But here the point is, not every variable is equally probable. That is the reason we are doing fx x dx, because whatever will come, that depends on fx x, right? So that is the reason we are doing fx x dx. Okay, so that's the reason I wrote that expectation is average, it's mean, it's fast movement, everything is same. It's mean only. But if the random variables are not equally probable, then we have to go with the density function integration. Okay, if it is equally probable, that means no problem. You sum them all and then divide by it. Okay. And then expectation of a function gx with the PDF fxx is gx fxx dx. Okay. And what about moments? Moments of nth order moment is e of xn is minus infinity to plus infinity x to the power n fxx dx. Very simple. But you note it, this is moment, not the central moment. For central moment, we subtract the mean from it. So this is nth order moment. Okay, not central moment. Now, if we go with discrete random variable, what is that? Okay, so for discrete random variable, PDF can be written as fxx equals to summation of px xk delta x minus xk. This is important notation. I will explain it, because this notation, when we read particle filter, this notation is borrowed. Okay, what is the meaning of this fxx? Fxx is the discrete random variable, and if you want to written in terms of probability mass function. So what is probability mass function? Probability mass function is px of xk. That means the probability. And where delta of x minus xk. That means delta is the delta function. X minus xk means at xk its value is 1. Other place there is no value. Okay. So if it is x1, we will get the value of px of x1, that probability. If it is x2, we will get delta of x minus x2, that probability. So it represents a probability is a expectation. Then how it will be expectation? Then xk into px of xk. That means these values, random values into their probability, sum of all. So probability means what? That how it will occur. So if all the probabilities 100 into 1 by 6 plus 200 into 1 by 6 plus 300 into 1 by 6, we make them all and then we'll get the expectation. Okay. So this one we'll see this expectation we'll see when we are doing the filtering. So then with the discrete points and weights, we are doing this expectation. So later we'll come here. So everything is very directly related with this basics what we read. And what about the moment? Moment is the summation of x to the power n px xk. It is nth order moment, right? So zeroth order moment is 1, first order moment is mean, second order moment is variance. If it is, there it depends. It's the central moments also comes. We'll come to it. Now it's a central moment. So what is the nth order central moment? Nth order central moment is expectation of x minus mu x to the power n. That means x minus mu x to the power n, and x follows a PDF fx of x dx and integration minus infinity to plus infinity. Okay. So this is the central moment. Now the point is, what is the difference between moment and central moment? We are subtracting mu x. So central moment always we subtract mu x. Why? Because to remove the bias. If mu x is 0, that is fine. If it is not 0, we have to remove the bias. That means mu is the bias. Okay, so we remove the bias and then we calculate the nth order moment, and that is become central moment. For discrete random variable, how we will calculate the central moment? It is expectation of x minus mu x to the power n equals to the summation of x minus mu x to the power n into probability mass function px of xk. That means at xk, what is the probability? P is the probability. Capital P is the probability. What is the probability? And then x minus mu to the power n. N we will fix either it is first order, second order, or something. If it is second, n is 0 means 1. And if n is 1, that means x minus mu x, which is mu x, so it will be 0. And it is second order moment, we have some meaning, which is variance, x minus mu x square, which is variance. Okay. So there in note, I try to write that in central moments, the mean is subtracted in order to remove the bias due to mean. Okay. Suppose if we have a signal which is not zero mean, so let's say it's vibrating about some value, then if you average it, that is the bias. So you have to reduce the bias. You have to subtract the bias. So that is the region of central moment we used to do. And zeroth central moment is 1. First central moment is E of x minus mu x, which is E of x minus mu x equals to 0. And the second central moment is called variance. And we have third central moment for central moment as well. Now this is conditional expectation. So what is conditional expectation? So for a continuous random variable, conditional expectation is the expectation over the conditional PDF. Now you see it is written expectation x if x given a x dx. That means we need to determine the conditional density function f of x given a. Then we have to calculate x into f of x given a x dx. Very simple. And for a arbitrary function gx, the conditional the expectation will be e of gx given a will be equals to minus infinity to plus infinity gx f of x given a x dx. Okay, that's all. So for discrete random variable, what is then we need to do the discrete PMF, conditional PMF, P of x given a at the point small x. So expectation of x given a will be equals to summation over xk P probability of x given a at the point xk. Is it making sense up to this point, up to this slide, right? It's very simple, basic, but we feel that it will be good if we brush the basic to start with. Now till now what we did up to this point, we did the single dimensional random variable. Now we might have the multiple random variable. That means it's not a single dimensional. It could be any dimensional. So then what will be the joint? Then their distribution is joint distribution because it is multi-dimensional. So the joint cumulative distribution function of a pair of random variables x, y is f of x comma y. We will write like this: f of x comma y, f of x comma y in bracket small x comma small y. At the point small x small y will be equals to probability when x is less than equals to small x and capital Y is less than equals to small y. That is the probability. And then it means that CDF of joint probability of two events that jointly x will be less than x and y will be less than y. Okay. So that for any number of n number of variables, what we could write? We could write f of x1, x2, dot, dot, xn will be equals to probability of x less than x1, x2, x2 less than small x2, and capital Xn less than small xn. So that's all, right? So this is joint CDF. And what about the joint PDF? We know that if you take derivative, we will get PDF. So joint PDF is small. PDF means small f. Small f. Joint of what? x1, x2, dot, dot, xn, random variable. At the point small x1, small x2, dot, dot, small xn will be equals to n number of derivative into f. That means CDF of where x, capital X1 is less than small x1, capital X2 is less than small x2, like this. Okay, so this is the n dimensional because we need multiple random variable because we need to work in a multiple random variable. Okay, single will not be helpful to our work. So we are gradually proceeding to multiple random variables. Now then what will be the joint PDF? Joint PDF of x1, x2, dot, dot, sorry, it should be xn will be equals to probability of at x equals to x1, x2 equals to x2, xn equals to xn. Like if you think about xy, that means probability of x1 is x1, x2 equals to x2. That means it is a point on space. So what is the probability in the points on surface? If it is 3 dimension, what is the probability of some point in space? And more dimension we cannot say, but conceptually you could visualize. So that means each point is on space. Either it is surface for 1 dimension, it is on line, for like this example we gave, and for 2 dimension it is on surface, for 3 dimension it is on space, and so on. Right? Now the marginal PDF. This is also important. Sometimes we don't get full PDF, we marginalize it. Marginal means we reduce the number of random variables. How? Suppose we think about that we have n number of random variable dealing with, but at some point we need x1, x2 dot dot xm, where m is less than n. Then what we do? After m, those many random variables are there, we make integration. So it is called marginalization. So you see here it is, we are marginalizing. Actually, we have n dimensional, capital N dimensional PDF, and then we are marginalizing to capital M. So what we are doing? Capital N minus capital M, that many variables we are integrating. That's all. You see, dxm plus 1, dxm plus 2 dot dot dxn. We are integrating. So we are marginalizing. So if we have n dimensional PDF and we marginalize it to capital M, which is less than capital N, so we marginalize it to some lower dimensional PDF. Okay, sometimes it is important. Suppose we have a two-dimensional PDF, we marginalize it to one-dimensional PDF. That means other dimension is, we take that it can take from minus infinity to plus infinity, any value. Only one variable we are interested with. Here we are interested with capital M number of variables. So other variables, capital N minus capital M, can goes any can take any value. So we are integrating minus infinity to plus infinity. So that we are doing the marginalization. That is called the marginalized. Okay. Now this is a very cumbersome way of writing, because if we have n number of variables, we have to write x1, x2, x3 dot 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 xn. Very so note. So what we do, this note is important. For multi-dimensional random variable, we define a vector capital X. Sometimes it is defined with a bold face X, where X is in Rn, and X will be equals to what? X1, x2 dot dot xn. That means we take the whole set of random variable as a vector, and then we write a vector. That notation is quite easy to write. Okay, so this capital X is a vector which takes the n number of random variables. Now it is interesting. So joint multivariate Gaussian distribution. So Gaussian distribution I already know first 1D, but for multiple random variables we could write the multivariate Gaussian distribution, which is n of mu comma sigma, where mu is the mean and sigma is the covariance, and its joint density function is given as 1 by 2 pi to the power n determinant of sigma e to the power half x minus mu sigma inverse x minus mu transpose. Now here you see. So fx, what should be the fx? Fx is a scalar, because fx is the PDF. You might have the multiple random variables, but when you reach to these x1, x2, x3 at that point, you have a PDF of another axis. So if you think about Gaussian distribution in 2D, we have x-axis, we have y-axis, we have a random variable on the surface, but the PDF is on the z-axis. So PDF is single, it is scalar. Okay. So now if you see 1 by 2 pi, it's scalar, mod determinant of sigma, it's a number, no problem. Then if you do, suppose there is no sigma, if you do x minus mu, and this you will get e to the power something. Now the important thing is that here what is the mean? Mean is the mu. So what is the dimension? Dimension is n cross 1. So mean is a vector, because mean means it a point on the space. So it has to be a vector. And then what is the sigma? Sigma is a matrix. So what is the dimension of the matrix sigma? Dimension is n cross n. If it is n dimensional random variable Gaussian distribution, dimension of sigma is n cross n. Okay, that is called the covariance matrix. Now what the values means? So you have a diagonal. So diagonals are actually the variance of between similar variable x1, variance of x1, variance of x2. And then what about the off diagonal term? They are the correlation. If the random variables are not correlated, then off diagonal terms will be 0. And if it is correlated, then diagonal terms will be, off diagonal terms will be something. Correlated means if some random variable x1 increases and x2 will increase or decrease, there is a correlation. So in that case, you see, so what is this? Sigma is very important thing. So sigma, what is the properties of sigma? Sigma is an n cross n dimensional matrix, which is symmetrical. Okay, because the correlation between x1 and x2 will be correlation between x2 and x1. So it is symmetrical. Okay, and then diagonal terms represents the variance, and off diagonal term represents the correlation. Now let's see. Suppose we have a two-dimensional Gaussian distribution. Okay. So if we have a two-dimensional Gaussian distribution, a Collins Collins वो है वो सफाई वाला पेपर. So suppose we have a so if we see how the Gaussian distribution would look like, it's a kind of Bell shape, two-dimensional I'm drawing, right? Like this Bell shape, right? And we have something x-axis, y-axis, right? So now, if we do the projection means suppose you cut the bed horizontal to the surface, you will get a surface. So if your sigma is diagonal, that means sigma has this term and these terms are zero. That means there is no correlation. You will get a circle. Okay. So when there is correlation, this circle will get taper like this. If there is a correlation, because x depends on y. And then if you do so, then the distribution will look like this correlation, and on the top there is a p like this. Okay, so that is interesting. So if it is not correlated, then it is a circle. So we used to give that assignment to students, that write a program and then you show that it is a contour is a circle, and then if it is correlation is there, it's not a contour. And if the correlation is more, this circle, this ellipse will become more sharp. Okay, so that is kind of little bit intuition. Okay, so what's the time? We think, yeah, lots of things are finished. But interesting thing will come in random process, which is very confusing to everybody. Okay, so the joint movement is very, it's nice, similar. So expectation of x to the power m and y to the power n will be like x to the power m, y to the power n, f x y, dx dy like this. So it is not very interesting. So now random process. This is very interesting. Okay, I want to spend some time on it because random process people are too much confused. Okay, so I'll try to explain it. So before going to random process, so random process, random signal, stochastic process, all are same. So let's say, what is the deterministic signal? So you all know that what is the deterministic signal. Let's say I give some example. Let's say 5 sine 20t. 5 sine 20t. So you take any particular t, you will get a number. And again, you take that t after some days or sometimes you will get the same number. So with time, at a fixed particular time, the number is not varying. It is fixed. So it is deterministic signal, right? Now you consider a signal, right? It is very interesting. So, okay, na? So it is now, so deterministic signal we all know. So we read deterministic signal where BTech second year, signals and system class, right? Now we'll go to random signal. What does it mean? Random signal is, let's say xt is a sine 20t, right? And what is a? A is the outcome or random variable or outcome of an experiment. Okay. So we defined a signal like this. Let's say we have a die and we roll the die. And then whatever is coming, A is that number. 1 may come, 2 may come, 3 may come. That means, suppose you first roll a die, 1, right? And then 1 sine, let's say 1 comes, 1 sine 20t. You take some value of t. You will get a number. Now, again you roll die. You might get 6 here. So then 60 sine 20t. You take the same t, but your number is different. So your signal is not deterministic. At some point of time, you are doing the same thing, but your signal amplitude is different. Okay, and that is random because the signal amplitude is a function of an outcome of an experiment, and you don't know what will be the outcome. Okay, so that is the random signal. So there are two things. One is deterministic signal. That's what I wrote. some signal may exist whose amplitude is different for different trial at a particular time t. T is particular, but at different trial, it's a different values. Okay, that means you do something, make a trial, you come and you see this is the value. On another day, you come, you make a trial, and then the value is different. So that means the signal is not deterministic. Okay, at same point of time, the signal can take different values. That is interesting, right? So then what is the random process? We are defining. Let's say a random process is a function of the elements of a sample space as well as another independent variable t given an experiment E with the sample space S. The random process xt maps each possible outcome zeta belong to x to a function x of t comma zeta. I'll try to explain it on board. Let's say we have a die rolling, right? One may come, that means zeta 1. This is sample space, zeta 2, and so on, and zeta n, right? And then we have some signals, let's say t versus x of t comma zeta. Why I'm writing t comma zeta? Because x is the amplitude, is a function of t as well as the zeta. Let's say zeta 1 comes, okay? Then the signal is, let's say, like this, right? Then say, let's say zeta 2 comes, then x t comma zeta. Then the signal is, let's say, different. Then similarly comes like this. Then let's say zeta n, then signal is x t comma, this is zeta 1, t comma zeta 2, and so on, t comma zeta n, and that is t versus x. It may be something different, right? So you see, now it's interesting. So we have an outcome. So the signal is not only the function of time, but it is a function of zeta. That means, so that is what written very specifically. So a random process is a function of the elements of a sample space, is a function of elements of the sample space. So these zeta are the elements of the sample space. So as another independent variable t, and also function of another independent variable t, given an experiment E, we did an experiment with the sample space, and the random process xt maps the each possible outcome zeta to x of t comma zeta. Is it now clear, that definition? So that means random process is a process such that, so it maps xt, deterministic signal is xt only, there is no zeta, but it is xt comma zeta. That means the random process is a process which depends, or the signal which depends on time as well as the outcome of an experiment. Okay. So now let's note the random process is not a single signal. So in deterministic process, a sine omega t, it's a single function, right? But random process is not a single because it can be x t comma zeta 1, x t comma zeta 2. So the random process is a family of signal. Okay. So deterministic signal is the only signal, no family, individual signal, but random process is a family of signal. Okay. In that process, there are many such signal, many signal comes. Okay. So now there are a few things. So now say, so all these are all possible outcomes, t zeta 1, t zeta 2, t zeta n. So this is called ensemble. Okay, all possible outcomes. So t zeta 1, this is called ensemble. So it is written, a ensemble is a set of all possible realization of a random process. So x t zeta 1, x t zeta 2, dot dot x t zeta n is an ensemble. Collection of this, I wrote second bracket, that means set of this is an ensemble. That means all the signals makes an ensemble. Okay, ensemble is a very tricky, means very important word. Now, why the difficulties? Difficulties is sometimes people do statistics over ensemble. Sometimes people do statistics over time, and it's very confusing. So that is the reason I think due to ensemble only, random process becomes very confusing. Okay, so now I'll make everything clear. So now you see, so sometimes we write second point note, xi t Sometimes we make some simplification of the notation. Sometimes we make some simplification of the notation, which is xit equals to xt comma zeta I. So we remove zeta I. Instead of that, we write xi. That means ith realization in this second note. Okay, this way it can be written. So the random process, third, note 3, note first, the note 2, a random process or stochastic process is the collection of all sample functions. That means it is a collection of xt comma zeta. That means it is a collection of x1t. x1t means x1t comma zeta 1. That notation I am making it because that is the way it is used. x2t, that means xt comma zeta 2. Like xn means x t comma zeta n. Okay. So the representation of a random process, whether we call the car, maybe he is calling that car. Okay. So a random process, now last point, xti is a set of number or random variable at a particular time ti. xti is a set of number or random variable. Sometimes we write that xti, what is the ti? So that is another important thing. So now let's say what we have. So it's a family of signal. So that means it's a family of signal. What does it mean? That means one signal realization can be like this. It could be x1t, right? Another could be another realization. It is x2t and so on. And we'll get tx nt, which is like this. Okay. Okay. So now what I'm trying to say, xti is the set of all number of random variable at particular time ti. Let's say at time ti of t1, what is the value? This one, x1, t1. Same time, at time t1, it is the value x2, t1, and so on. And at time t1, it is the value xn, t1. Okay. So you see, at time t1, there are some values. So that is represented as xti. So it is a set of random variables. These values are also random variables. Right? So we take this one. So this is the values across the ensemble. This is the values across the ensemble. So if I say xti, that means it is the values across the ensemble at the point ti. Okay. So now how we can represent a random process? There are different ways we could represent. First thing is that a complete description of ensemble. That means all the ensemble we can say, and the complete description is the random process. Next thing could be with a single realization. That means only one process, x, t, comma, zeta I, only one. We call that a single realization, right? And then over the ensemble for a fixed time, that means x, ti, comma, zeta, that over the ensemble for a fixed time, okay? And with a single random variable x, ti, comma, zeta I. That means how we can represent with all the ensemble. That is a complete description. We can represent with a single realization, this one or this one or this one, right? We can represent a particular time, but the points are over the ensemble. And we can represent with the t1 and x zeta, a single number. Okay. But the random process means it's a collection of all realization, which is called the ensemble. So that is interesting. So due to these two things, now it is confusing that sometimes it goes over time, sometimes it goes over ensemble. So when we are doing operation over the random variable or random process, we need to first thing we need to keep in mind what we are doing. We are doing over the time or over the ensemble. I think if you think this way and then read, it is easy to understand. Okay. Now the complete description. Complete description means so how a random process can be described. So First thing is the complete description. That means, let's say at some point of time, we have this population, right? At another point of time, T2, let's see, T2, we have this population, right? Another time of T3, we have this population. So now the random process, if we want to describe it completely, we need to describe the joint PDF of the numbers at T1, T2, T3, .. So it's written, you see, a random process is completely described by the joint distribution of xt1, xt2, xtl, where T1, T2, TL is, I think, yes, sorry, I think from Bale somebody. Yes, yes, hey, अभी पढ़ना आ गए, कोई दिक्कत नहीं है, यू टेल, यू आस्क देम टू कम ब्लॉक 9. अच्छा अच्छा, इसीलिए फोन कर रहा है. अच्छा, आई एम आस्किंग स्टूडेंट्स. ओके ओके, ठीक. हाँ ठीक ठीक ठीक. हाँ, मेरा नाम भेज दीजिए. हाँ, कोई दिक्कत नहीं. हाँ हाँ. Oh, actually, some 4 persons are coming from bail to attend the course, and security stopped them. You call the security. You take this mobile. So security actually did not allow them to. Sorry. So wala dekho, they are calling this number. You take, you call. Probably security number. है ना? Okay sir. एक तो अब सिक्योरिटी नंबर है ना इधर से, नहीं इधर से आप सिक्योरिटी नंबर को कॉल कीजिए, बोलिए कि आप भी कॉल कर दीजिए, बोलिए कि कोर्स है उसको आने दीजिए. So they got, I'm not picking phone now, so they are becoming mad. Security is not allowing. So, okay, so let's come to this point. So then how we can describe completely? We can describe the process completely if we describe with a joint distribution among all the time. Suppose this process, say a discrete process, we have time T1, T2, T3, TL, and how this random process can be described? If we can describe the joint distribution of T1, T2, T3, T4, TL, right? So that is the reason it is written f of xt1, xt2, xtl. X means over the ensemble. Okay, then it will become the complete description. But it is very difficult to completely describe. So such a description of random process is cumbersome and extremely difficult and impossible. Okay. So if you want to describe it, so then it is completely cumbersome and then almost impossible, because so much times how you will define a joint distribution, it will become a very large distribution PDF, right? So what the reason we take some shortcut. So there are two things which are very important: mean and autocorrelation. Okay. So mean means mean over the ensemble. Again, it's a confusion. In book, it is written only mean. They never mention it is over ensemble. Okay, mean over ensemble is the mu x ti. That means at ith sample, ith time is expectation of x ti, which is x fx ti. That means if we have a distribution here, which is fx ti, we do the calculate mean over this. Okay, if we want to calculate mean, that means mean over the ensemble. Mean over the ensemble. And then autocorrelation function means expectation between the two time. So x of T1, that means at T1 whole population, at T2 whole population, and expectation of xt1 and xt2 will give you the autocorrelation. And how will you get it? You have x1, x2 and the joint distribution between x1 and x2. So f of x1, x2, x1, x2, dx1, dx2. Okay, these two things are very, very important. So we don't go with the complete description, rather we'll go with the mean and autocorrelation function. Okay. So for tau equals to T1 minus T2, autocorrelation function is expressed as Rxx T comma T, because T1 and T2 both are time. So we can go T1 to T1 plus tau. So then Rxx T plus tau. That is simple. Will be equals to Rxx tau. This we can written Rxx tau. That means E of xt into E of xt plus tau. Okay. Please. Right. Rxx T1 T2 is the E of xt and xt plus tau. So that means if we have a distribution of x1 x2 fx1 fx2, so then it will be E of xt1 into xt2. So if you have joint distribution, you are making minus infinity to plus infinity, it will not be a matrix. You see that integration is going on. xt1 is xt into xt, but you have to do xt plus tau, and then you have to do the expectation of that. Okay, it is scalar. So if you see x1 x2 f x1 fx2 of this, and you are making integration minus infinity to plus infinity, so it will be scalar only. Right. Yeah, but another thing. Okay, I'll see. In some a problem, there is one book which is called Reddy. There is some book on probability, random process. They solved a lot of problems. Reddy book we used to solve from there. So what is the book name? What is Reddy? Which is Mallikarjun Reddy. Yeah. Okay. Probability and some random process. Mallikarjun Reddy. So it's a kind of 600 pages book, and it consists of so many problems, only problem solving. So that is quite interesting book. Okay, so it is scalar. So E of xi is equals to one step, and then this is 2, then x1, x2, dx1, dx2, rxt, comma, it is scalar. Okay. So now let's see. So now there are two things. One is strict sense stationary. What does it mean? Strict sense stationary process, SSS. So a random variable is called strict sense stationary if the joint distribution x1, x2, dot dot xn will be equals to the joint distribution of t1 t plus tau. That means if you have, let's say we take this two ensembles, we calculate a joint distribution, and then we shift t1 plus tau and t2 plus tau, and then we make a joint distribution of that. So this, if they both are same, they call the strict sense stationary. That means joint PDF is not changing when you are shifting the time. That is the thing. T1, T2, and here T1 plus tau. That means you have a ensembles, and then you are shifting the whole ensemble to T plus tau, but the joint PDF is not changing. That means it is a stationary process, but it is strict sense stationary. But getting strict sense stationary is very difficult. So we work with wide sense stationary, WSS. So what is WSS process? If mu x is constant and autocorrelation function is a function of tau, then it is called WSS process. Okay, so we give some example. Will come. So this is called the WSS process. So it is, I don't know. Okay, so it is called the WSS process. So now if we see the wide sense stationary WSS when mu x, so we give some example that you can say whether it is WSS or not, then we calculate mu x if it is constant, and then autocorrelation function is a function of tau. Tau is time. So you see this is okay. So then it is called the WSS process. Then the few two things are important. One is ergodicity and another is Markov process. So what is ergodic process? First, this process has to be WSS. And then if it is ergodic, if the ensemble average of the process can be calculated using time average. What is the meaning? So now we have two things. One is ensemble average, another is time average. Now we calculate the ensemble average and we calculate the time average. Time average means single realization. If both are same, okay, and ergodic in autocorrelation, if A means ensemble average, not E. A means ensemble, E means so ensemble average and the time average are same. And then ergodic in autocorrelation means if the autocorrelation of xt plus tau will be equals to E of xt plus tau. That means autocorrelation in time and then autocorrelation over ensemble are same, then we call it ergodicity. So what is the importance of ergodic process? If we have an ergodic process, we don't need to have the whole ensemble. Rather, only single realization is enough, because on single realization we'll calculate mean, on single realization we'll calculate the autocorrelation, and that is more than sufficient. Okay, so sometimes we assume the process is ergodic. So now there is some homework I wrote. Consider a random process xt equals to a sine omega t plus theta, where theta is the uniform distribution from 0 to 2 pi. Is it a WSS? So for that, you need to calculate the expectation and autocorrelation, and you have to see whether it is a WSS or not. Is it ergodic? So for that, you have to calculate the mean and the autocorrelation. If mean is satisfied, you will say that it is ergodic in mean. If autocorrelation is satisfied, you will say that it is ergodic in autocorrelation. So that's
that about A, not B.
Huh?
About A.
No, A means the average over the ensemble, and E means the average over the time. Oh, homework. No, A you can take anything. It's a constant. It does not matter. No, theta is not constant. Theta, phase. Phase is a function of U. Uniform distribution, 0 to 2 pi. Phase is different, na? So it's a random process. Okay, so what is Markov process? Suppose we have a random process xt is said to be first order Markov if fx of xtn plus 1 less than xn given xtn. So what I want to say, so the probability of this given all the previous things, xtn plus 1, xtn plus 2, xt1, okay, is same as xtn plus 1 given xn plus 1 given xn equals to x. That means it depends only on the previous state, not before that. So that is called the first order Markov process. So we will assume our state estimation problem as a first order Markov process. Okay, so that will be our assumption. So that some notation might be wrong, I guess. xt1 equals to x1 equals to this something is missing. I think it's not printed. So it will be fx xtn minus 1 given this, and all those things you could forget. That means it depends only on the n. This one you can forget. Then only it is the first order Markov process. Okay. So and then we summarize. It's already time is over. Yes, 10 minutes anyway. So somehow it's within the time. So what we learn? We learn about the probability and density function. We learn about the multivariate random variable. We learn about the moments, central moments. We learn about multivariate Gaussian distribution. We learn about conditional density. We learn about random process, stationary process, WSS, ergodicity, and Markov process. So I think this is sufficient introduction to go ahead. So then after some time we'll start second lecture. Okay. Thank you. Any question you can ask, informally also you can ask.